Okay. So finally, the total response is this form. We obtain the particular response and homogeneous response for the system. The homogeneous response, as I explained, is similar to the previous chapter. You need to form the characteristic equation, or you can use the formula. Here you can see the general form for the homogeneous response. As you can see, the frequency of the homogeneous response is omega d, and also we have x naught and phi naught, which are amplitude and the angle phase respectively for the homogeneous response, and you can obtain them from the initial condition. And this part, which is the particular response, x cosine omega t minus phi, which omega is the frequency of excitation, and x and phi are the amplitude and the angle phase respectively for the particular response, and they will be obtained by substituting into the main equation. So if you substitute and simplify and extract the results for these coefficients, you can obtain, according to the initial condition and the form of the equation of motion, you can extract x naught and phi naught, which are the coefficients, constant coefficients for the homogeneous response. So this is the general formula to obtain the total response. Consider this is a total response. I mean, it includes the homogeneous response and particular response. And also you can determine the response of the system by using the theory of ODEs, and you can directly solve the equation of motion. So in the theory of ODEs, you need to form the characteristic equation, find the roots of the characteristic equation, and then you know that the homogeneous response is equal to the C1 cosine, exponential of alpha 1 t, which alpha 1 is the roots of characteristic equation, plus C2 exponential alpha 2 t, which alpha 2 is the second root of characteristic equation. And for the particular response, based on the form of the non-homogeneous terms, we can predict the general form of the particular response. For example, when the excitation is cosine omega t, the particular response is a combination of cosine omega t and sine omega t. And we can consider C1, for example, cosine omega t plus C2 sine omega t. And then we can plug in the main equation and obtain the numerical value for C1 and C2, the coefficients of cosine omega t and sine omega t. Or we can consider in this form in only a cosine function or sine function. So it's up to you that which method you prefer, and then you can solve the equation of motion. So let's continue with several examples. First, consider in the first example, we want to consider a spring mass damper system with K 4000, M is equal to 10 kilogram, and C is 40 Newton second per meter. Find the steady state and total response of the system under the harmonic force 200 cosine 15t Newton, and the initial condition of x naught is 0.1 and v naught is 0. So we have an ODE from order 2. The form of the equation is mx double dot, which m is 10, plus cx dot, which c is 40, plus kx, which is k is 4000. It's equal to ft, which is 200 cosine 15t, with the initial condition x naught and v naught. So we only need to solve an ODE from order 2 and obtain the homogeneous and particular response, because we need to obtain the steady state and total response. So you can use the previous formula in the last slide, but Here we will solve directly the equation of motion. As you can see, this is the equation of motion. Mx double dot plus Cx dot plus Kx is equal to Ft. We can substitute from the numerical value of the given data, and we can extract this form for the equation of motion. So this is the main equation, and we need to solve this equation with this initial condition x naught and v naught. So to obtain the homogeneous response, we need to form the characteristic equation. The characteristic equation is the coefficient of x double dot multiplied by alpha squared plus the coefficient of x dot multiplied by alpha plus the coefficient of x, and it's equal to 0 because we are solving the homogeneous equation. So we assume that in the right hand side of the equation we don't have any non-homogeneous term. So alpha 1 and alpha 2 can be obtained using the delta method, and the roots of this equation are -2 plus -19.9 I. So the real part is -2, and we know when the real part is negative, so the response will be stable, and the imaginary part is 19.9. So the homogeneous response is exponential of real part times by t, which is -2, multiplied by C1 cosine imaginary part time by t, and plus C2 sine 19.90. So this is the homogeneous response XH, and C1 and C2 will be obtained from the initial condition. XP, or the particular response, will be predict from the non-homogeneous term. Here you can see the non-homogeneous term is 200 cosine 15t. It means the frequency of the excitation is 15. So as you can see, the particular response is a combination of cosine and sine with the frequency of excitation, which is 15, and we consider a cosine 15t plus b sine 15t. Now we need to obtain a and b by substituting into the main equation. This is the main equation. So we need to calculate xp dot and xp double dot. Xp double dot, which is the second derivative of xp with respect to time, and xp dot is the first derivative of xp with respect to time. The first derivative of xp with respect to time is a cosine 15t. The derivative of cosine 15t is minus 15 times by sine 15t, and the derivative of sine 15t is 15 times by cosine 15t. So this is the x dot, xp dot in fact, and the xp double dot is the second derivative, so it will be equal to minus a times by 15 squared times by cosine 50 plus b, of course we will have one negative, so it will be minus b times by 15 squared times by sine 15t. So we can plug in into the main equation and xp, which is in this form, and then we can collect for cosine and sine functions. The coefficient of cosine in the left hand side must be equal to the coefficient of cosine in the right hand side, which is 200. This is the first equation. And then the coefficient of sine 15t in the left hand side must be equal to the coefficient of sine in the right hand side, which is 0. So you can see, and this is the second equation, the coefficient of sine 15t, and the first one is the coefficient of cosine 15t. So we have a system of two algebraic equations with two unknowns a and b. We can easily solve these two equations. For example, from the equation 2, you can obtain a is equal to 1750 divided by 600, and then we can substitute into the first equation and obtain b, and then again we can find a. So we can solve these two equations for a and b, and finally the particular response which will be obtained in this form. So a is 0.1022, Here you can see in this xpt, we substitute a is equal to this value and b is equal to 0.035. So this is the particular response. We have the homogeneous response as well. So the total response is the summation of the homogeneous plus particular. So here you can see this is the xt. And another important point that most of the time the students forget is that the initial condition must be applied to the total response, not only to the homogeneous response. Sometimes the students, when they want to obtain C1 and C2, here when they extract the homogeneous response, they use this initial condition and apply this initial condition to the XH and find C1 and C2. But in fact, these initial conditions must be applied to the total response here to this xt, not to xh. Sometimes when the particular response is 0 or we don't have any non-homogeneous term or we don't have any external excitation, the xh is equal to xt. So we can apply the initial condition to xh because both of them are the same. But in these type of problems, when we have external force, when we have force vibration response xp, so the total solution or the total response is the summation of xp and xh. So to obtain the constant coefficient in the homogeneous response, we need to find xt, the total response, and apply the initial condition to this xt. Now we have xt. To obtain C1 and C2, we can use these two initial condition. At t is equal to 0, x must be equal to 0.1. So here in this xt, we can substitute t is equal to 0. So this exponential minus 2t will be 1. Cosine of 0 is 1. Sine of 0 is 0. Here cosine as of 15t is 1 and sine of 15t which is 0. So we will have C1 plus 0.1022. It must be equal to 0.1 and then we can find C1. And to find the C2, we need to obtain the first derivative of xt. The derivative of this xt is equal to, here we can divide it into two separated parts. The first part is this term, the derivative of this term, and the second part is the derivative of this term. For the first part here, the first one, the derivative of first type is, because this is a combination of exponential and cosine functions and sine function. So the derivative of this term is equal to the derivative of the exponential term, this term, which the exponential of minus 2t, the derivative of exponential minus 2t is equal to minus 2 times by exponential minus 2t, multiplied by these parentheses, and plus the derivative of the parentheses multiplied by the exponential term. So this is the derivative of first part. And the derivative of the second part, it's easy because there is no exponential term here. So the derivative of this term, the derivative of cosine 15t is minus 15 sine 15t. And the derivative of sine 15t, which is 15 times by cosine 15t. So you can easily find the derivative of the second part. So once you find the derivative of xt, then you can substitute t is equal to 0 and it must be equal to 0 because the second initial condition, the velocity at t is equal to 0, must be equal to 0. So we can substitute and finally we can find the c sub 2. So we can use these two equations to obtain C1 and C2. From the x naught or the first initial condition, we find C1, and from the second one, we can find C2. And finally, you can substitute, and this is the general form for xt, which is exponential minus 2t, and times by this is C1 and C2 plus the particular response. This is the particular response. And also, again, I should mention that you can use the formula to find the total response, the formula that I explained in previous slide. Okay, any question from this example? Is it clear? Okay. As I told you, you can use the formula. To use the formula, you need to obtain omega n, and also you can find the static deflection, delta st. You can find the damping ratio because we have c, k, and m, and easily you can find the frequency of damp system, and then you can substitute into the equation for the particular response, and also you can find the homogeneous response by using this equation and find x naught and phi naught. So it's up to you, and you can use these forms and this formula to find the response. The second example, a moment m naught sine omega t is applied to the end of the bar as shown here. You can see we have a bar, a rigid bar, which is subjected to this moment m naught sine omega t. Determine the maximum value of m naught, which is the amplitude of the external moment, such that the steady state amplitude of angular oscillation does not exceed 10 degree if omega is equal to 500 RPM. So the frequency of the excitation is 500 RPM, and we need to obtain m naught such that the steady state amplitude, or x, the amplitude of the particular response of the angular oscillation, does not exceed 10 degree. Of course, we need to convert it into radian. K is 7 kilonewton per meter. This is the stiffness of the springs. C is 650 Newton second per meter. This is the coefficient of damping, this C. And L is 1.2. The total length is 1.2 meter, and the mass of the bar is 15 kilogram. So we need to extract the equation of motion. In this system, as I told you and I explained yesterday, we need to first extract the equation of motion, because when you write the equation of motion, the coefficient of x double dot, or the coefficient of the acceleration, is not m. We need to find the equivalent m. Okay, so here we have a rigid body which is rotating about this fixed point O. So we can write the moment equation about point O, and similar to the example that I solved yesterday, we know that in this case, because the weight of the bar creates some initial deflection in these two springs, so we neglect the weight into the equation of motion and into the free body diagram, and also we ignore the initial deflection in these two springs. So we can assume that this bar is moving in theta direction, in clockwise direction. So when it's rotating in clockwise direction, the force in this spring, in this K, will be in this direction. This is the free body diagram. And the second spring, 2K, with the stiffness 2K, will be in upward direction, the force in this force. And also the force in the damper will be in upward direction, because this bar is rotating in clockwise direction. So, and also we have two reactions at the pin O, which when you write the moment equation about point O, these two forces will not appear. And finally, it must be equal to the mass moment of inertia about point O times by the angular acceleration. Also, you can write in the right hand side from dynamics, you know, when you are writing the moment equation about a fixed point, in the right hand side you can write that the mass moment of inertia about that fixed point times by angular acceleration, or you can write the mass moment of inertia about the mass center times by the angular acceleration plus m times by the acceleration times by d, which d is the distance between the fixed point and the mass center. So you can write it in different form, but the simplest form is writing about the fixed point. So we will have three forces and three moments. The moment due to this force K is K times by L over 4 times by theta. This is the force in this spring. And the moment about point O, this force must be multiplied by the arm, which arm is L over 4. So it will be K times by L over 4 theta. This is the force in the spring, and L over 4, which is the arm of this force. And also we have one negative because the moment due to this force about point O is in counterclockwise direction, and we assume that the clockwise direction is positive for the theta. The second force is the force in the damper. We know that the velocity of this point is L over 4 theta dot. So this force is C times by L over 4 theta dot and multiplied by its arm, which is this length, and this length is again L over 4. So this is the moment due to the damper about point O. And again, you can see we have one negative sign because the moment due to this damper about point O is again in counterclockwise direction. And the last one is the moment due to this spring with a stiffness 2K. The force in this spring is 2K times by the displacement of this point. And the displacement of this point is L over 4 plus L over 2 times by theta, or 3L over 4 theta. And the moment due to this force about point O is this force multiplied by its arm, which is this length, and this length is again L over 4 plus L over 2, or 3L divided by 4. And this is the third moment. And again, we have one negative sign due to the direction of the moment. And also we have one external moment, m naught sine omega t, which is in positive direction. As you can see, it's in positive direction of motion, so it will be positive. And finally, all of these moments must be equal to the mass moment of inertia about the point O multiplied by the angular acceleration. So this is the equation of motion for the system, for the rotational motion about pin O. And now we need to solve this equation. So when we have the equation of motion, we can find a particular response for this equation. We need to obtain the numerical value. As you know, JO is the mass moment of inertia about pin O, and it's equal to the mass moment of inertia about the mass center, which is for a bar is 1 over 12 times by ml squared plus md squared, which d is the distance between point O and the mass center, and it's equal to L over 4. In this problem, if you look at here, you can see that the mass center is here. Exactly, this is the mass center of the bar, and this is the point O. So the distance between these 2 points, which we call it d, is equal to L over 4. So this is the d into the equation for JO, or the mass moment of inertia about point O. We have the value, numerical value for M, L, and D. We can substitute and solve and obtain J naught. And also we can substitute the numerical value into the main equation. So we can finally extract the equation of motion in this form. And also we know that omega is 500 rpm, or we need to convert it into radian per second. As I explained, we need to multiply by 2 pi and divided by 60. It will be in radian per second, which is 52.35 radian per second. So we have this equation of motion, and now we need to obtain the particular response, because according to the problem description, we need to obtain the m naught when x has a maximum value of 10 degree. So theta p is equal to x cosine omega t minus phi, which x is m naught divided by, this is from the equation, from the formula, and also we have the phi for the particular response. So please pay attention. This is the particular response, or steady state response. It's not a total solution. Okay, we are only discussing the particular response in this problem. So we need to obtain m naught when x is maximum. It has a maximum value of 10 degree. So we can substitute the equivalent stiffness, mass, and C. As you know, the equivalent K is in fact the coefficient of theta. Here you can see this is the equivalent K. The equivalent mass, which is the coefficient of theta double dot, and the equivalent C, which is the coefficient of theta dot. So you can substitute here, and also we have omega, which is 52.35. This is the frequency of excitation. So you need to only substitute the numerical value and simplify. And finally, we can extract this equation for the amplitude. This amplitude must be less than 10 degree, or the maximum value for the amplitude is 10 degrees. So we need to convert it into radian. For this purpose, you need to multiply by pi divided by 180. And this is the radian value for the degree. And then you can find that m naught must be less than this value. I mean, when you substitute for x, because x is equal to this fraction, and it's equal to m naught divided by 4,529. So m naught must be less than 790.55. And this is the limitation for m naught. So if m naught was more than this value, for example, m naught was 800, then x will be more than 10 degree. Okay, clear? Any question? Okay. Okay, the last example is we want to find the steady state response. Again, pay attention. We want to obtain the steady state response. It means that only we need to obtain the particular response. So we don't need to find the homogeneous response of the system shown for the following data. K1 is 1 kilonewton per meter. K2 is 0.5 kilonewton per meter, and C is 500 Newton second per meter. The mass of this particle is 10 kilogram. The radius of the pulley is 5 centimeter, or 0.05 meter. J naught, which is the mass moment of inertia for this pulley about the mass center, or about the point O, is 1 kilogram meter squared. And F naught, which is 15 Newton. Omega is 20 radian per second. So we have this external force, which is F naught sine omega t. So we need to obtain the particular response. First of all, the first question is that what is the degree of freedom for this system? And how many degree of freedom we have in this system? Here we have theta and also xt. To find the equation of motion, the main important question is to obtain the degree of freedom, because according to the number of the degree of freedom, we will find equation of motion. For example, here, if we assume this is a 2 degree of freedom, so the equation of motion will be include 2 equations, or it will be a system of 2 ordinary differential equations. But definitely it will be a single degree of freedom because we are discussing the STOF systems. So this is STOF system, but here we have a rotation and also we have a translational motion. And we need to find a relation between this rotational motion and this translational motion of this particle M, because we have 2 particles or 2 body. One is this particle with mass M and the other one is this pulley, okay, with mass moment of inertia 1 kilogram meter squared. So it's very important to consider the degree of freedom and find a relation between this rotation and this translational motion. If we assume that here, this point, the displacement of this point is xt and it's equal to the displacement of particle with mass m, then we can find the relation between xt and theta, because here we know that the displacement of this point is equal to 2, sorry, it's equal to 2 times by r times by theta. So we can consider that xt is equal to 2r theta. And using this equation and this relation, we can find only one equation of motion for this system. But we need to plot the free body diagram for both the pulley and the mass, and also find the tension in this cable. And by finding this relation, we can find only one equation of motion, which includes the motion of the pulley as well as the motion of this mass M. So let's plot the free body diagram. And if you plot the free body diagram for the pulley and for the mass M, we will have a tension T in these 2 particles. This tension T must be calculated from one equation and then substitute into the second particle to find the equation of motion. And in fact, this T, this tension, is the relation between the motion of the pulley and the mass M. So if you write the moment equation for this pulley, you can write the moment equation about point O, because this pulley has a pure rotational motion about point O. So the moment about point O must be equal to the mass moment of inertia about this point multiplied by the angular acceleration. So if you plot the free body diagram for this pulley, we will have one force due to this spring K2, one moment due to this force T, and also we have the weight, and here at this point we have the reactions of pin O, but all of them, because they pass through the point O, they will not appear into the moment equation. So the moment equation is the force due to the spring K2. The force in the spring is K2 times by the displacement of this point, which is r theta, and multiply by its arm, which the arm, because we are calculating the moment about point O, so the arm is this length and it's equal to r. So this is the moment due to the spring with the stiffness K2, and we have a negative sign here, as you can see. The second one is the moment due to the force T, and the arm is 2r, because the arm, when you are calculating the moment about point O, the arm is this length for force T or the tension T, and it will be T times by 2r. When we assume that the positive direction of motion is clockwise, so the moment due to the spring K2 is negative, but the moment due to the tension T will be positive, because you can see the moment will be in clockwise direction. And finally, it must be equal to J naught theta double dot. So from here, we can find that T is equal to this term. As you can see, we find a relation between T, the mass, moment of inertia, and angular acceleration of this pulley. And now we need to write a equation of motion for this particle with mass M. This mass has only a translational motion, so we need to write the force equation in vertical direction. The force equation in vertical direction must be equal to mx double dot. We assume that this mass is going down, so we will have the tension T, which is in upward direction, so it will be negative. We will have one force of a spring. When this mass is going down, the force of the spring and the force of the damper will be in upward direction. So because we assume that xt positive direction is downward, so the force in the spring and in the damper will have a negative sign. So it will be minus k1 times by x minus c times by x dot plus f, which is the external force, and it's in positive direction of motion. It must be equal to mx double dot. So we can substitute T, because here we have T from the first equation. Once you substitute T, you can extract the equation of motion. But as you can see, this equation is a function of theta as well as x. And from the first point that I mentioned, we can find a relation between x and theta. And this is the equation of motion, and we have x and theta. So we can substitute that x is equal to 2 times by r theta. And then, so from here, we can conclude that, for example, x dot is equal to 2r theta dot. Yes, because x is equal to 2 times by r theta. So x dot is 2r theta dot, and also x double dot is equal to 2r theta double dot. And conversely, theta dot, for example, is equal to x dot divided by 2r, or theta double dot is equal to x double dot divided by 2r. So it's up to you that which one do you prefer, and then you can find the equation of motion as a function of x or theta. So it's up to you. So we can substitute and finally extract the equation of motion. Here I extract the equation of motion as a function of x, and substitute instead of theta, I substitute x divided by 2r. And this is the equation of motion. And we need to solve this equation. So to solve this equation, we need to substitute the numerical value for m, k, r, j naught, and c. And finally, this is the equation of motion for your system. So to find the steady state response according to the problem description, or the particular response, because the non-homogeneous term is 5 sine 20t, so we can consider that the particular response is a sine 20t plus b cosine 20t, or a cosine 20t plus b sine 20t. This is the particular response. We need to substitute into the main equation. This is the main equation. We need to find x dot, xp dot, and xp double dot, and then substitute here. 11 times by xp double dot, 50 times by xp dot, and finally 112.5 times by xp. As you can see, this value 11 is the equivalent mass. This is the equivalent damping constant, and this is the equivalent stiffness, or K equivalent, for your system. So the next step, we can substitute xp dot and xp double dot. As you know, xp dot is minus 20a sine 20t plus 20b cosine 20t. And finally, the xp double dot is minus a 20 squared times by cosine 20t plus minus b 20 squared times by sine 20t. And then when you substitute here, you can collect based on cosine and sine. and it must be equal to the right hand side of the equation. Of course, here I move the 5 sine 20t or the non-homogeneous term to the left hand side of the equation. As you can see, this is 5 times by sine 20t. So the coefficient of cosine and sine must be equal to 0. So we have two equations with two unknowns a and b. And once you solve these two equations, you can obtain that a is equal to this value, and also you can extract the numerical value for b. And this is your particular response. As you can see, the particular response is a combination of cosine and sine functions with the frequency of 20t, and the frequency of excitation is exactly the same as the frequency of the particular response. Okay, any question? Is it clear? If you don't have any question, we can wrap up this session, and after a short break, we can continue for the tutorial. Okay, so I will wrap up this session, and after 10 minutes break, I will start the tutorial session. Thank you.